Welcome. We're going to get into sets again. So I'm going to review sets a little bit, some basic notation, set theory, talk again about set operators, and talk about them in terms of Venn diagrams. I'm going to try to work the Venn diagrams in throughout the process, but we'll save it as a punchline in the end just to go back over stuff. So as a quick reminder, what is a set? A set is an unordered collection of elements. And examples are a set of the vowels in the English language, A, E, I, O, U, or the first 7 prime numbers. Again, both these have an order because we write them naturally with order. Many of us write letters in alphabetical order and numbers in either ascending or descending order, but sets do not require that. There is no need for that. So when we're describing sets, again, there are two main notations. Set roster notation. This is where you literally list everything out, or using ellipses to kind of imply the pattern that is a continuum forever. This latter one kind of sucks because you have to assume that, and that is always bad to make assumptions. The other one is set builder notation, where we have something like this, where we have X, a vertical line that means such that X equals 2n, comma, or where, or and, n is, and we'll talk about this little e right here. It actually means, this ironically is set notation. That is the set notation for n is an element in Z, and Z is a set of integers. So again, you don't need to know what this is. We'll get to that, some of these that I'm using inside here because they just have them. Sometimes in your book, more commonly, again, just so you can understand this, you have two options generally. One is this kind of vertical line, and one's this semicolon or colon. I can never keep the two dots versus the line. They're the same notation. It's kind of you pick and choose which one you want, and people use it. So this first one, by the way, is a set of all integers, even integers. This one's a set of all odd, but this is again the natural numbers, and we'll talk more about those basic concepts like that. So some common universal sets are these right here, where R is a set of all real numbers, Z is a set of integers, positive and negative, Z plus is the positive integers, N is the natural numbers including 0, Q is the rational numbers, where that means you have an integer over an integer and the denominator is not 0. So these are the most common ones that we are going to leverage over and over again. We have a couple others, but these are the primary ones. I'm just going to assume that you know, practice, get comfortable with them. So let's talk about something that we've not talked about yet, equality of sets. So suppose I have two sets, A and B. How do I know if they're equal? Only if they have the exact same elements. So this actually is a great example. 1, 2, 3, and 3, 2, 1 are the same elements in a different order. 1, 2, 1, 3, 2 is also the same set because it doesn't matter if I repeat 1 or if I repeat the 2. They're still the same set. In addition to that, we have a couple of special sets that are really, really important. Namely, what's called the universal set. Usually this is U, and this is like the sandbox of all the sets I'm dealing with. And then we have the empty set. And again, do not, on any of the exams or any of that, use this for 0. This is not 0. This is the empty set. Use it for 0. I will get mad at you. It's not okay. That's bad notation. Sometimes we just write braces that are empty. Again, sets are written with braces. It's common notation. So these are our two common sets. And we'll talk more about them, but the empty set and the universal set kind of play the ultimate roles. So whatever space I'm working in, the universal set is kind of the biggest thing I could be, and the empty set is obviously the smallest you can be when you have absolutely nothing in it. So let's talk about subsets for a second. A subset, and there's two ways to do it. This subset, where I use, it's kind of a U on its side. And if you look at this, it looks a lot like, again, I mentioned this when we did this way back, introduced sets. This looks a lot like the inequality symbol. So this looks a lot like this symbol right here. Well, because of that, it's not really something that is a big way, but this means it could be. But a subset is a subset only if every element in A is an element in B. Or again, using our we now know about predicate notation, for all X, if X is in A, then X is in B. And again, this little E symbol is an element of or contained within, depends on which expression you prefer. So there's two ways to explain it, and that's kind of the key thing. So let's talk about the properties of our empty set. First, the empty set is a subset of every single set. That's actually really, really easy. For all elements in the subset, I have to show their elements in that. Well, for all X inside of this, then X is inside S. That is trivially true because there's no elements in the empty set. Therefore, that's X contained in there is always false. If the initial condition is false in a predicate, the whole thing is false. Therefore, the implication is true. All right. So again, I'm simply using our own logic to understand stuff. Another crazy subset property that's really important is every set is a subset of itself. Again, all I have to do is consider this for every X in here. So that means I have to show that for every X inside of S, X is in S. That's obviously true because of just say, suppose X is in S, then X is in S. It's kind of silly. But two sets are equal to each other. Remember I mentioned it before if they have the same elements. And this also can relate that they are equal if they are subsets of each other. So often how we prove, if I give you two sets and I say I want them to be equal, I have to show arbitrarily, but in general, that all the subsets of one, all the elements of one are this in the second set, and then flip it and suppose that they're an element in the second set and show that's an element in the first set. So we got to, even no matter how we define it, we have to kind of work through it that way. Now, there is also something called a proper subset, and that is when we just drop the equality. And that is any subset where they are not equal. Simply that. And here's a quick example. If A is 1, 2, 3 and B is 1, 2, 3, 4, 5, is A a proper set of B? The answer to this is, well, yes. All right. Now let's talk a little more. There's another set property we really haven't talked a ton about, but it comes up. It's called cardinality. And cardinality is how many things there are. So let S be a set, and if there are exactly n elements in S, where n is any non-negative integer, we can say that S is a finite set, and that n is the cardinality of that set. So I'm counting up the number of distinct or different things that kind of help us. So let's look at this. What is the cardinality of this set A, B, C? Well, it's 3 because there's exactly 3 distinct or different things. What about this? What's the cardinality of this? So this is in set builder notation. Remember that n, and I know this didn't come out, but this n right here is all the natural numbers starting at 0. So that means this is all the numbers up to 100, including 0. If it was just from 1 to 100, that would be 100. But because there is that 0 in there, this actually, this is a typo. That should be 101. Because you have 0, 1, 2 to 100, and all of this is 100 elements, and this is the extra element in there. So yeah, that's a typo. This should be 101. I apologize for that typo. All right. What about how many things are in the empty set? Well, the empty set has nothing in it, so its cardinality is 0. It's the only thing with cardinality. All right, so we have cardinality. It's really useful. I'm going to quickly mention this. This is something I'm going to spend a lot of time on, but what is an infinite set? An infinite set is any set that is not finite, meaning If I took its cardinality, that's not an actual number because it's infinite. There's a more defined terminology to infinite, and there's different cardinalities of infinite. That's a massive area of set theory, and we could just go down a huge pipe. I won't do that right now, but there's different kinds of infinite. And part of that is because some of the infinite sets we have are the natural numbers, the integers, the rational numbers, and the real numbers. And just think about that for a second. All natural numbers are integers. So therefore, this infinite is bigger than this infinite. Q has even more numbers than Z. In fact, between A and two integers, there is an infinite number. So that's kind of like infinite times infinite. Ugh. So this is horrible. And then real is even bigger than that. So again, these are just simply some infinite sets. That's all you need to know. Their cardinality sucks. All right, let's do some more cardinality examples. Here's a question. What is the cardinality of A? Well, you should say 4. It has the elements. Let's just highlight them. It has 1, 2, the set of 1, and the set 1, 2. So it has 4 things. What about this? What is the cardinality of B? It's 2. That one's a little bit easier because the set 2 kind of doesn't throw you off. What about C? What is the cardinality of C? Hopefully you said 2, because remember, the repeated 2s are ignored. And what about this one? The cardinality of 5n, where n is any real number. Well, that's an infinite set, because I took an infinite set and I multiplied each one by 5. It's still infinite. That's just awkward. What about this last one? What if I say 5n, where n are all integers? It's again an infinite set. We can kind of move off it. All right, so cardinality is kind of an important thing. We're going to get into something in the upcoming sections on, we're going to talk about functions, and this is where cardinality is going to play a little bit of a role in it. All right, let's talk more about something called a power set. So a power set is a set of all subsets of P. So if I give you the set S, which equals ABC, what's the power set? Well, the empty set, we've already said, is a subset. The sets A, B, and C by themselves, take each element and just make it its own set. Those are subsets. What if I pick pairs of A and B, and then A and C, and then B and C, those, and then what about the whole thing? Because remember, it is still a subset. Not proper, but it is a subset. We didn't say anything about proper. We just said it had to be a subset. So we have this. And in fact, something that we will talk about later on when we count, you can notice real quickly, I have 3 things here. And I have 1, 2, 3, 4, 5, 6, 7, 8. It turns out that there is exactly 2 to the n elements in every power set if the original set had n elements. Let's do more with power sets. All right, so let's consider the power set. S is the empty set. What's the power set of the empty set? It's just the empty set. It's super boring. And the reason being because the only subset is itself. Because now what if I do, what's the cardinality of that? It is 1. So while the cardinality of the empty set is 0, the cardinality of its power set is 1. It's crazy. Okay, what about here? S equals 1. What's the power set of 1? Well, that's actually just going to be, there should be a comma between those two, but that should be the empty set and 1, and thus the cardinality is 2. So we kind of see this trend going on, and we kind of play with it. What if I do 1, 2? Again, you should have 4 of them. 0, the empty set, 1, 2, and 1, 1, 2 a set. And again, we have 4. And from here, 3. We already did this with the ABC, really. And so we have 8. And from this, we can confirm the fact that this rule is 2 to the nth power. So this is we can do an induction on this and talk about it more. say, what if it's already true? And then you kind of do an inductive proof. There's a combinatorial proof and a lot of other ways to attack this one. Don't worry about it. I just want you to know what are power sets and can you find them? All right, let's go back to set operators. We did this way back, so I'm going to kind of blast through this, but I'm going to do some Venn diagrams to illustrate some things. What is a union? Well, a union means it's in A or B, or it's in both. So here I have A is 1, 2, 3, 6, and B is 2, 4, 6, 9. So AB is this combination right here. But another way to look at this, what is a union? Well, let's draw a different picture. I'm going to make a circle here and call this circle A. I'm going to draw this circle here and call this circle set B. So all of A is within this circle on the left, and all of B is within the circle on the right. With this, then the union of these two is going to be the combination of everything that is in them. So this purple would be A union B. Or if I was to color it, it's going to color it all the way in. So that is what A union B is everything in A and everything in B. So Venn diagrams are really useful to look at as long as you don't have more than 3 sets. I'll tell you right now, trying to look at them with more than 3 sets really gets hard. So what's intersection? Intersection, again, is the elements that are in both. And in a Venn diagram, again, let's look at A and B. Do the same Venn diagram. Here's A, here's B. This middle overlapping chunk is A intersect B. So the Venn diagram, we can look at these things and kind of understand what they look like. So again, let me clear this out and give you the example. I'll put it in. So let's use the exact same numbers. So what would that look like in terms of a Venn diagram? All right, so what would this Venn diagram look like? Well, again, we have 2 circles. Here's A and here's B. Now, this is the interesting part. When you draw Venn diagrams, we have to figure out what is their intercept, because I have to put 1, 2, 3, and 6 somewhere in A, and I have to put 2, 4, 6, and 9. However, this is the problem with Venn diagrams. To draw them properly, we have to put their overlap or their intersection right here, which is 2 and 6. And then since we don't want repeated terms, we then get rid of them in the other lists. So we have 1 and 3 still hanging out here, and 4 and 9 over here. And then you can see more clearly how these actually work together. And if you're given a Venn diagram, it's very easy to read it and say, hey, I can see what the intersection is. It's just 2, 6. That's at 2, 6. We just list the elements in it. But this is the downside, is it's, again, really hard to do this if you got a whole bunch of elements and not really clear. All right, so let's talk about generalization of unions. So suppose I have a whole bunch of unions. Again, this is like for all. So if I do this, this looks like the summation notation and the product notation we did before, but it's a union notation of all those index sets. So if AI is 1 through I is, then the union is really A1 would be A1, A2 would be A12, A3 would be A13. And this gets the idea that a union is always going to make something bigger. And so if you're unioning a whole bunch of things that are actually within each other, you just get the biggest one. Now, intersections, we can do the exact same thing. I'm not going to test you hard, but this is a good thing to think about. What if I want to intersect them? Well, let's use the same thing. And that's just 1, because this is saying what is in all of these sets. Well, this set is this A1 is going to be the smallest one with just 1. A2 is going to have 1, 2. So we have to throw out the 2. And then we combine with 3 and so forth. It's just always going to be 1. So we have these things we're building on over and over and over again. Now this gets us into an idea known as partitions of sets. Partitions means we are going to have two sets that are disjoint, or in other words, their intersection is empty. And if A and B are disjoint, if and only if their intersection is empty, if they're mutually disjoint, then we actually refer to them as partitions. So a partition is a bunch of mutually disjoint things. All of you computer scientists should think about this. When you partition a hard drive, you're not sharing parts of the hard drive. You're setting aside these specific bits over here are for this specific operating system or whatever, and these bits over here. And you cannot share them. You can have copies in both, but we want them mutually disjoint. We don't actually want to be sharing things. So partitioning a set, if I'm partitioning a set, I'm going to break it up into a bunch of other sets in that way. All right, so cardinality of sets, of the union sets. This one's kind of an interesting property, and it's one that people sometimes don't understand. Obviously, if I union, I'm going to take everything from A and everything from B, but the problem is we also have to subtract everything that's in their intersection. So again, let me just go back to an example that I already did, but I'm going to do it one more time. I'm going to show you. So let's look at this. This set right here, where we had A, and it was the set 1, 2, 4, and 3. I know I did them out of order. And we have B, which was the set 2, 4, 6, and 9. All right, so 2 and 4 are in here, and I have 1 and 3 hanging out over here, and 6 and 9 over here. Well, notice the cardinality of A is 4. The cardinality of B is 4. However, the cardinality of A union B is how many things in this total space? Well, it's only 6 of them. But that is not equal to 4 plus 4, which would be 8. The reason being, when we counted everything in A, we counted up including this middle section. So we counted actually these numbers. When we counted B, we counted these numbers again, which means these middle numbers got counted twice. So I have to subtract them out. And indeed, when you do 4 plus 4 minus 2, you get 6. So that is why this formula comes in. It plays a major role later on in what's called the principle of inclusion-exclusion. It's a really, really valuable idea. We can generalize it because principle of inclusion-exclusion goes more than just 2 sets. It can go multiple sets. But the idea is anytime I'm counting up the union, there's no really great rule for counting up the intersection. That's the problem. I mean, I guess you could rewrite this equation to say that, but yeah, it wouldn't really help you. All right, so let's get to one other concept I want to massively nail, and it's the difference of sets. So set difference, and again, your book sometimes does a minus sign. That's not the common notation. It usually uses backslash. And it's everything that's in A that's not in B. So what is this set? So let's just draw a quick picture. This is set A. This is set B. And I'm going to color in. I'm going to switch colors. This highlighted red part, that highlighted red part, that is A minus B. So notice I just took A and I simply took away the portion right here that was in the intersection. So because of this, we can just take away the intersection. It makes our lives a lot easier, and we can kind of go from there. All right, I hope that helps you. Let me know what questions you have. Good luck.